Hey, welcome to the show, Frank.
Hey, Duncan.
Now, I would hope that anyone who's listening to the Unexplored Territory knows who you are because, of course, you're one of the co-hosts, for a very long time. But for those who recently started listening, who's Frank Denneman and what do you do for Broadcom/VMware?
So my title is what's called a distinguished engineer. I work for the AI and Advanced Services team, and so we're responsible for AI services within the VCF stack. Well, that's a little bit too broad, right? Because there are a lot of teams within VCF. Look at storage, for example, and so each have their own AI focus. I am tasked to do the cross team coordination of things. So from a AI knowledge center, pretty much, to the rest of the organization to help the VCF platform grow towards an AI platform.
So if our team starts talking about AA, the storage guys, they've probably spoken with you recently.
Yeah, well, yeah, actually, the rest of my afternoon, I have storage people on my calendar. So yeah,
Yeah,
correct.
I kind of had that feeling already because I'm going to be at the tech advisory board next week, and there's a lot of storage and AI related topics on the
Yeah,
agenda. I noticed.
yeah,
Now, of course, we're not going to discuss that because all of that is still secret. But one of the things that I did briefly want to discuss because we just both came from a event called VMAC Connect in Amsterdam. It was held for the very first time. I did the keynote yesterday, and we had about roughly 500 people, slightly more, in the room from 20 different countries. So I think that was really cool. You were there as well. You were there on Tuesday, and of course, you were there today as well. How was the event
yeah.
for you?
Good. It was a first for 3 days, a VMUG event. One of the key things, like you said, were like 20 customers. I spoke with Brad. He talked about 26 or 28 countries. So I think it became a very international event. The only thing that I didn't see that much were Dutch people. And so it was in Amsterdam, yet the majority of people were non-Dutch speaking persons because on Tuesday, I had this workshop for 2 hours, and I asked, like, can I do this in Dutch or should I talk in English? Like, who doesn't speak Dutch? And 80% of the hands basically went up, like, yeah, no Dutch here. So I had, of course, luckily, I had to do it in English, but yeah, so it was really interesting, and so I did the 2 hours or roughly 2 hours on Tuesday, and I had a breakout session today, which was 45 minutes, and I basically took most of the content for the 2 hours and I crammed it into the 45 minutes. So these people well, I have some pity for them that I basically blasted through that content in 45 minutes.
Yeah, they were probably cooked. And were you speaking at what level? Duncan Epping fast or William Lamb fast? Because
No,
that's a
William Lamb
completely
fast,
different
like
level.
Usain Bolt, William Lamb.
sprinting from stop to finish. Now, yeah, it's something that I noticed as well. A lot of different, well, a lot of people from different countries. I did meet a lot of Dutch people, but I was there on Wednesday, so
Yeah,
maybe some of them actually came out for just a day. I'm not sure about that. I didn't really ask people if they were there for multiple days or not, so I didn't really notice that. But I would say at least the majority of sessions that I went to and the conversations that I had, people were very positive.
mhm.
Also, the people that came from abroad, for them, of course, going to Amsterdam is a treat. For most Dutch people, well, except for you
Not a
because
treat.
except for you because you live close to it. But for people like myself who have to travel for 2.5 hours,
Yeah,
yeah, I mean, I could do without it. But it is what it is. I just told Brad as well, the organizer, of course, of the event, that I thought it was a fantastic event, and especially for the very first edition, right?
yeah,
If you look at the setup of the solutions exchange, the session rooms, just the
yeah.
general vibe. It all felt, like a VMUG on steroids, basically.
Yeah, it was a good event, and like you said, right? I live close by, so for me it was a 20-minute drive. So if I compare the last VMUG where I had to fly for, well, I traveled for 13 hours. I did a keynote for 45 minutes, and then basically went on a plane back the same amount of hours. This was a delight, put that way.
So they're also doing another 4 or 5 events in the US. I don't know
Yeah,
if you want to do any of those, but if you want
I
to,
wish them all good luck.
so you have no desire to fly to Minneapolis
No,
again.
no, and to be honest, look, if I think like Hawk, it won't make any financial sense. There are a lot of people inside the US. who can cover the functionality. There are many different persons within the AI teams at field level, at sales level, and so they should spearhead this effort in on the continent of the US for sure. If it's South America, I think that's a different discussion, which we already had in the past, anyways, right?
Yeah, of course. I wouldn't mind visiting, Argentina, Brazil,
Exactly.
well, even
Yeah.
Mexico, it doesn't really matter,
Yeah,
any
I
of
would
those
make a
countries.
exception for that one. Yeah.
I'll also make an exception for VMUG Japan, by the way. So if you guys are listening, VMUG Japan, invite me.
Yes. Yes. And of course VMUG Hawaii,
Of
right?
course, yeah.
Yeah.
That's the
So
best one.
yeah.
For sure. Now, we're not going to talk about VMUGs today. We're
No.
going to talk about GPUs and how GPUs are consumed by AI workloads and the
Yeah.
complexity that comes with that.
Yeah.
Now, that's probably a good starting point.
Mhm.
Even at the event, I had a whole bunch of conversations because, of course, in my slide deck, AI popped up a few times as well. And I was wondering, it's probably, as I said, a good starting point first to explain what some of the problems are that customers are facing today when it comes to these GPU attached or GPU related workloads like
Yeah.
AI.
Yeah. So we can start infrastructure up, or we can start, or we can look application down. And so if we look application down, it's finding the first use case. Like everybody wants to do AI, everybody sees the value of AI. Okay, but how can you actually create something that shows value to the business that makes sense also from an investment perspective, because these things are not cheap. The whole infrastructure is not cheap, and does your data center actually have the capability from a power perspective, from a cooling perspective, and all of these things, right? And then, of course, this is the big elephant in the room. What are you going to do with your data, right? First of all, it's typically private data that you want to use for your first POC, for your experiment, and so you need to think about that as well. Now, if you dig a little bit more deeper into that as well, is that data is stored. I don't have to tell you this in many different ways inside the organization. We always had trouble finding data. We always had trouble then accessing the data. And now the third angle is the quality of the data. It can be very good for a human. Might not be as good to do this at a automated level where you can actually derive answers or make conclusions out of the data that is presented. So there's a data quality issue as well, right? Now, if you would basically, if you have covered that, then we start to dive into the infrastructure. We start looking at a data center design, of course, with all what I said about the power consumption and about the energy, about the cooling. What type of server do you need? What is the configuration? And then the big one for the audience is, how do I actually manage all of this? Because that's a topic by itself.
The funny thing is that we've seen similar challenges in the past when it came to, when virtual machines were kind of new, or
Yeah.
virtualization was just brought into the market. And of course, we saw some challenges around that as well, especially from a CPU and memory perspective.
Yeah.
They probably are, the challenges were probably similar to what we are facing with GPUs today. But of course, a GPU is a completely different beast. Actually,
Yeah.
yesterday at the VMA Connect event, I was talking to Intel, and one of the guys also was mentioned, or they actually had a talk which more or less was on that topic. Now, for those who are listening, it's probably also good to explain, what is so different about managing GPU resources versus GPU resources. Because if you look at CPU resources, well, most of us have been doing that for 20 years already. But
Yeah.
GPU,
Not
I
so much.
had a couple of systems with the GPU in there for 12 to 18 months.
Yeah.
But that's it. I don't even have any experience with it. So why is it that different?
Yeah, you didn't do it at scale, and you already had some
Exactly,
issues, right? At the gas level, and then at
for
the lower
sure.
level. Okay, so let's start off with the basics first, right? So you and me have been in this industry for 20 years, right? So we've been basically used to thinking about CPU and memory as there are these resources, and these resources can be oversubscribed. These resources, even if you don't design for it, let's say you say, I won't ever oversubscribe my memory, then that's your choice, but there's still the capability in the system itself, in the platform itself. Think about maintenance mode, think about HA events, think about affinity rule going wrong, I don't know, right? But the reality is, even if you design for it, that you're not going to use oversubscription, you still have the ability to do so, and the system has the ability to do so. So you're not locked out. You don't have placement issues. You don't have all of these problems that will interfere with your day-to-day operations, right? And here's the key, and this is the most important thing. If you have free capacity, if you see free capacity in your dashboard, that typically means it's usable. Well, we can talk about HA and admission control and all of these things, but in general, meaning if I see the system has 70% is 70% utilized, I can still use 20 or 30% easily, right? And I can oversubscribe, and I can basically trust particular functionalities that will allow to do prioritization and to do some form of quality of service. It's not the case with GPUs. First of all, there is no oversubscription in GPUs. If you use the three different methods, you have a pass-through, meaning you go to expose a physical device into a virtual machine and you allow the virtual machine to manage that device. That's a one-to-one relationship. If you then go to vGPU, for example, you have what's called fractional GPUs, where you take a portion of a full GPU, or you can have full GPUs or multi-GPUs functionality. Each of these components, they will have some placement restrictions, some topology awareness that you need to take into account, and especially when you go to fractional, where you can say, I want to use this GPU and assign it to a multiple VMs, and I'm going to use a vGPU profile, which has a little bit of compute and a little bit of memory, and I will basically make use of the different workload patterns in the GPU to basically get a good performance. But if you have 80 gigs of memory inside the GPU, there is no way to allocate 100 gigs or provision 100 gigs. It is literally what's on the card can be provisioned once or allocated once, and that's it, even if those virtual machines are not using it. Now, you can say, if people understand time slicing and MIG, you can say, no, that's not entirely true. Correct, right? Because if we do time slice, we do time slicing on the compute level. So you have the 80 gigs again. I'm going to use a profile with 20 gigs of resources. That portion will be allocated to that virtual machine from the moment it starts to the moment it powers down. Even if it doesn't use it, it's there for that particular virtual machine, right? Where that's something that the vGPU driver will decide. But then, if it needs to use the GPU for its computations, with time slice, it will wait its turn. Then it basically can use the entire compute, and its memory portion will feed that compute part. Now, the moment some other VM wants to run, they need to schedule, right? And so it's time slicing. So the next slice will be for the other virtual machine, and it can compute based on the memory slice it has on that device. Now, when it comes to MIG, multi-instance GPU, it's a hardware isolation pattern, meaning I'm going to create multiple slices inside my GPU, and that is assigned both compute and memory 24/7, or as long as the lifecycle of the virtual machine lasts, to that particular virtual machine. If it's idle, nobody else can use it. If it is active, it's the only virtual machine in that area of computer memory that can use it. So it's a very deterministic way, but it's a very strict way of chopping up a card, right? So depending on your workload, you either choose one or the other. Now, if you then take one step further, you need to think about placement on a GPU, placement of workload in a host with multiple GPUs, and placement for a virtual machine in the cluster. And there are all these profiles, all these policies that will have an impact on where it's placed, where the GPU is compatible with the workload requirement. And so, in short, what you see from a free capacity perspective does not always mean that it's useful, right? So there is this mismatch where people are building dashboards and they'll say, okay, let's say I've got a terabyte of GPU memory in my cluster, but I only see 700 gigs being utilized. It can mean in certain situations that this is a very worst case scenario, but just to prove my point, it can be that you cannot power on any virtual machines anymore, even though you're staring at 300 gigs of underutilized space, due to the way things need to be placed, due to the way patterns appear from a policy perspective. And that's, I believe, one of the most difficult things. Understanding how your decision of profile choice will eventually drive to a lower utilization in your cluster.
You've spoken about these, or the option to have things configured in a pass-through manner, in a fractional manner as well. You talked about MIG. I don't know if that's similar to vGPU. We also have the dynamic model. Can you mix and match those models, or do you need to select one and you're stuck to that particular one as well?
It depends on, typically it's a per GPU decision. So I can have a host with 8 GPUs, and some of these are set to direct path, meaning I will basically allocate a full physical device to a virtual machine. I can have some virtual machines doing fractional GPUs, do MIG, but that's also a fractional GPU. Both are a vGPU construct. And I can assign some of them that they are open for multi-GPU functionality. It's a per GPU decision, whether that makes sense from managing things at scale, because we're so trained to think in homogeneous configurations inside virtualization that if you do this, then you typically need to dive in and drill into particular configurations per host. That will have an impact on operational aspects, on visibility aspects. So, because you could doesn't mean you should, right? But it's possible. If you have a use case that fits that, fine. It's supported.
Yeah, I think it's very valid to say that if you can, doesn't necessarily mean you need to do it. I just had one of those discussions with a vSphere customer as well. They were planning on adding additional devices to their hosts, and the new device that we're planning on introducing were 10 times bigger than the existing devices. And of course, we fully support that, but from an operational perspective, from a failure domain standpoint, it may not be smart. So I think that's very valid. Now, if you look at the stack itself, we also have, of course, solutions that help with scheduling and placement, like, for instance, DRS. So does DRS actually understand the whole GPU concept, and does it help you with the placement itself, or are you responsible and you need to do it manually? How does that work?
Yeah, so DRS is what we call GPU aware, meaning that we understand, or we as the royal we, DRS understands GPU, the existence of GPUs, but it won't use it primarily for load balancing. It's not a access where it's going to figure out the load balancing perspective. But what it does do is placement, and it does that very well. Now, does it do it all by itself? No. There's a construct called assignable hardware, and assignable hardware creates a list of compatible devices in each ESXi host, and it will basically bubble that information up to DRS. So each host will do that. And so DRS will get a good sense of what's available or not. And then depending on what type of GPU you have, the moment you're trying to place that virtual machine, DRS together with assignable hardware will create a compatibility list for that particular virtual machine. And then it will say, okay, these are the lists that are from a GPU perspective, these are compatible. Now, let me do my own magic. Let me figure out CPU, let me figure out memory, in certain cases, networking as well. And then say, okay, this is the best host possible for placing the virtual machine while it has the GPU resources. And I'm also aligning to the VM happiness of the VM and also the cluster load balance, right? So it's a combination of things. Now, if we then think about like the private AI services with the model runtime, we basically use that as the orchestration layer. And so when a data scientist says, I want to deploy this model endpoint, we basically work with DRS. So a VKS worker node is built, a VM class is used to basically allocate the GPUs. That's being sent to DRS. Give me a compatible host for these GPUs. And then the rest we start to orchestrate. We basically load the model from the model gallery into the virtual machine. We basically load it into GPU. We basically create an inference engine, and we send the model endpoint back to the user. And so you got this full orchestration by just providing you a desired state. I just want to run a virtual machine with some GPUs, and this is my model endpoint that I want to consume. Deal with it. And so DRS and assignable hardware and all the constructs in the vSphere cluster will start to work for you.
You've mentioned VKS, and of course, for those that are not aware, that is our Kubernetes-based platform, but that also has its own scheduling mechanism, as you said. So is there any potential for DRS and that scheduling mechanism to start interfering or start interrupting each other? Could there be any conflicts or whatever? Because typically, normally you wouldn't see two placement mechanisms stacked on top of each other, or do they deal with something different?
No. And that's the beauty of virtualized Kubernetes. So yeah, you have a scheduler inside your guest OS, inside your worker node. Typically that's Ubuntu. And then you have your normal case schedulers. But the reality of a virtual machine is that it's always a confined world of what the administrator exposes. Meaning, if I create a virtual machine and I use a VM class, and a VM class is like a template pattern. It's not a template in the sense of I'm using these bits and bytes. It's more a template, a resource template. Like I want to deploy a virtual machine with X amount of CPUs, X amount of memory, this storage policy, this amount of storage, and this GPU or these GPUs, right? Or a combination of GPUs and NICs and so on. Now, that becomes the source of truth, that virtual machine for Kates, for the Kubernetes scheduler. They don't understand that the host has 8 GPUs. What it sees is the underlying layer of the virtual machine. And let's say you basically selected the VM class with 4 GPUs. It will see those 4 GPUs. And that's only scheduling. We already allocated those GPUs to that particular virtual machine. Knock yourself out. Now, here's the key, and this is very, very interesting. If you think about this construct, we are relying on a situation where the administrator needs to predict the actual sizing, right? Now, that's one of the key things where we said with Base, let us expose a self-service portal where we can allow the customer to basically select the right VM class, and now they can basically deploy the VKS clusters themselves. But what we're also doing, and this is very important, this is basically the scheduling part that I want to zoom in to, is that in the previous versions, there was a very rudimentary vGPU scheduler, meaning I could, in my deployment YAML file, I could say, I want to have 1 GPU or 2 GPUs, right? That's a little bit too coarse because I might want to have a particular a particular container on a particular GPU, or I want to schedule something that has topology awareness. Now, we already have topology awareness with assignable hardware. If you have GPUs inside your ESXi host that are directly connected to each other through an NVLink, which is typically a hard cable, or through an NV switch, which is a whole mesh, then we understand that, and then we actually schedule the virtual machine aligned with the requirements of an NVLink or an NV switch. We isolate things, we make sure everything is correct, and we give you the best topology. Think about this. If you run a model, it has to communicate between multi-GPUs if you span it across multi-GPUs, and it has to do this on a continuous basis. So the topology matters. If you communicate through PCIe 5, you get 64 gigs of bandwidth. If you go through an NVLink or an NV switch, that's in modern architectures is 900 gigabytes or 1.8 terabytes of bandwidth, significantly faster, right? Now, you want to use that, so you need to have the platform to understand that topology. Now, what we're doing with the newer levels of VKS, we're the first Gates distribution that is AI compliant, meaning from the CNCF organization, they created like an AI compliance program, and one of these things is what's called DRA, dynamic resource allocation, and that allows the container to actually specify the required topology, and we will match that inside the VM as well. So we will expose the topology from a device group, and then it allows, with the DRA driver installed inside the guest OS, we will allow a container to actually use that topology instead of letting Linux guess where to place it.
Oh, that's a nice new acronym, DRA, and then combined with DRS. So it's going to cause some confusion, I guess.
Well, the problem, I don't even think DRA is the problem. It's the actual, the word next to it. It's called driver. If you talk to people who are into hardware and all of that stuff, driver is not the right term, right? Because it's not in the critical I/O path. It's not a managing aspect. It's just an orchestration thing. So a controller would have been a better word, but hey.
Yeah, it's not a driver, but it's driving something, more or less.
Exactly.
Yeah,
yes.
yeah. It's when you were explaining it, it actually made sense. But if I would see the acronym for the first time, I probably wouldn't understand it. Now, talking about things I didn't fully understand either, I was actually reading some of your blog posts, and you have a whole list. So I'm going to add all of them to the show notes because they are very valuable. But one of the things that stood out to me is that you were talking about different vGPU modes at some point in time, and you were talking about same size and mixed sizes. Now, I played around with vGPU a while back, but I can't recall having seen those different types. So maybe you can explain what it is and what it does and where that actually fits into this whole picture.
Yes. So same size and mixed size are for time slice vGPU profiles. It doesn't apply for full, it doesn't apply for mid, it doesn't apply for multi GPU. What it means is if you're going to deploy virtual machines with a fractional vGPU profile, we need to set a particular acceptance mode on the physical GPU inside the ESXi host. So per GPU, you can specify whether it will accept vGPU profiles with the same size, or vGPU profiles that are not in the same size. So we can mix these things, right? So the reason why you didn't see it is you didn't click through that layer inside the hypervisor or inside vCenter, I guess, right? It's not that obvious. So, but what it means is that it will impact what you can schedule and what you can place on the actual host and the actual GPU. So let's use an example of a host with 2 GPUs. And now I have 3 virtual machines. I've got a 10 gig, I got a 20 gig, and I got an 8 gig. Now, if I place these, if I put both the GPUs in the same size and I start the first one with 10 gig, it will land on one of these 2, right? Doesn't matter. Let's use the first one. Now, the second one is the 20 gig. It will be placed on the other one. Now, the 8 gig, there's enough room because let's say they are both 80 gigs, right? So I've got 160 gigs in total of free or of capacity, and I used 30. So I have 150 gigs in capacity. But because the profile is not aligned with the same size requirement, it cannot fit the 10 gig because it's not compatible with the 10 gig, doesn't fit the 20 gig. So you'll get a failed placement, right? Now, with mixed size, we say doesn't matter as long as it fits the GPU. So the 10 gig will be placed on one, the 20 gig will be placed probably on the second one, and the third one will be placed either on both, so either on 1 or 2. And so we can now start to mix and match. Is this perfect? No, it's not, because in order to actually place mixed sizes, we need to adhere to the actual logic inside the GPU. And so what we have are like slots, like HA slots, but then what we call it placement IDs. And every profile has a range of placement IDs. So the 10 gig has placement IDs, 20 gigs, 40 gigs, 8 gig, right? Now, if you place a 10 gig, it will probably start at 0. So you get 0 to 9. And so the next placement ID for 10 gigs is 10 to 19, so on until you reach to 79, right? 0 to 79 are 80 placement IDs. If I place 10 gigs and 20 gigs on the same GPU, my first placement ID, my first valid placement ID for the 20 is not 10, because placement IDs for 20 is 0 to 19, 20 to 39, until you get to 79, right? So my placement starts now at 20. So I actually have a gap of 10 in between. If I then basically deploy the 8 gig, it won't fit in between the 10 and the 20, because placement IDs start from 0 to 7, 8 to 15. Both are taken by the 10 gigs and the 50 and the 20 gigs. So my 8 gig will be placed on behind the first one after the 39, right, of the 20 gig. Still follow? Make sense what I'm saying?
Yep.
Okay. Now, if I now place a 40 gigs, won't be available anymore. Why? Because that 8 gig actually started to creep in that valid 40 gig placement ID, right? So that is one of the challenges, and that's what I meant with, because you see free capacity doesn't mean it's usable, right? So what I did, because I speak with a lot of customers, and we have a lab to develop things. And then I started to think, okay, I need to visualize all of this. So I actually created 2 tools that you can see what the impact is of your choice. Because it's easy to say it's all the fault of the profile. No, it's not. It's actually, if you understand placement IDs, you can also think about your profile catalog. You can say, okay, I got this 8 gig profile and I got this 10 gig profile. If I have like a workload that requires, for example, 7 gigs, in our right size mind, which we have talked about for 20 years, it would make sense to say, I'll give you an 8 gig profile, because I can then squeeze more workloads into the GPU, because I have got more, potentially, I've got 10 8 gig profiles in an 80 gig. But because you are mixing and you're not using a single profile, that doesn't add up anymore. And so now you need to think about, okay, maybe 8 gig is not the right choice. Yeah, I will basically slim fit my workload into that profile, but in order to right size at the cluster level, I actually need to think about the placement IDs and where they all line up. And so a 10 gig starts to make way more sense, because if I had that 10 gig and that 20 gig, and I had, instead of the 8 gig, I used the 10 gig, it would fall in between the 10 and the 20 again. And now I have room for the 40, right? So I made these visualizer where you can basically say, this is my catalog that I want to use. This is my GPU. Show me what it means, same size versus mix size. In mix size, show me what it means from a population perspective, whether I get siloed capacity, because that's the problem, right? The siloed capacity. You can see it. It's open. It's not available for everybody else. So yeah, you slim fit it, but you actually are wasting a lot of actual resources.
When I started reading some of the articles and you spoke about fragmentation, you spoke about these type of slot sizes, the placement, it really reminded me of the early days of HA, and I still recall some of the discussions that we had, some of the diagrams that we created. Of course, yeah, it's all in the various books that we published. Now, then when I went through the list of the articles and I read the next one and then the other one, of course, the tool popped up. Now, if I look at the tool itself, it really visualizes indeed what happens. And I think it also clearly demonstrates why a GPU is completely different than a CPU.
Yeah.
That it really visualizes that. But if I look at the tool, I can imagine that people use it to figure out, okay, will it actually work in my environment? What should the profiles look like? But can they also use it, for instance, to start sizing their environment? Because that's probably also a typical request you get. Okay, I've got these workloads. I probably end up buying these GPUs, but will that actually work? Can you use the tool for that as well? Or can you even say, these are the workloads, what should I buy?
Yeah, that's the $1 billion question right now in the market, because AI workload is extremely hard to predict. It's most of the it's so difficult, especially when you talk about language, right? So if you dive into the resource requirements of a large language model, and let's say you use it in a chat functionality. So if I ask a question like, "What's the capital of France?" It's a very simple question. It's a very straightforward answer, right? It's a short prompt, and it's a short generation of an answer. But if I ask, can you explain the relative theory to me like I'm a 5-year-old? It's quite a short question. It's an extremely long answer, right? Now, if these two questions are are basically sent to the large language models at the same time, we have what's called concurrency. I've got two sessions going at once. And now the first one is very fast. The second one is longer. Now, if you then take another example, which is one of the most common use cases right now in the enterprise, it's called RAG, retrieval augmented generation. So instead of relying on the information or the knowledge inside the model itself, you're going to create a database where you're going to store your own documents. And with every question that you ask, we will first start to retrieve answers or documentation out of the database, which is the retrieval part. And then we're going to augment that information with the prompt, with your question, and then we will send it to the large language model. And we'll say, hey, I've got this question. I've got all these resources you can use to generate the answer. Go figure it out. It's a very long context, right? Now, if you look at what actually is on the GPU, there are two main constructs. There's the static construct, meaning the weights of the model. That's a resident thing. That's always there. It's the first thing that loads, and that will consume a lot of the resource. So what you typically hear is a parameter count. Like this model is 80 billion parameters, or 120 billion parameters, and depending on the precision, it will consume a few bytes per weight, or it can use a half a byte per weight. And so typically the most common one right now, which will change in the future, but is FP16, 2 bytes per parameter. Meaning, if I load an 80 billion model, I need 140 gigs of static memory. It will always be there. Now, look at models, or look at GPUs. You typically need multiple GPUs actually to load that thing, right? Because the biggest one is 141 gig, so you have 1 gig left. That means that the dynamic part is actually the amount of memory available for usage. So the static part will load the capability of the brain, of the model. The rest is what you can do with it, like how many users can use it, what type of questions, and that's where the sizing typically goes wrong, right? What is all of this what you need to load? What are the questions? What are the answers? All of that. Now, to pile one on even more, is that we're now entering a durable agent era. So we first got ChatGPT, where everybody understood like this is tremendous, this is great, and now we're saying I don't want to deal with large language model on a day-to-day basis. I will use an agent, something that runs in the background and will figure out things for me. Right? The most popular thing today is called OpenClaw. And what OpenClaw does is nothing more than you create an agent for a particular task that you want to do, and it will continue to learn about your behaviors. Like, what do you want? Like, if you are, let's say you want to travel to the United States and you want to book that through your own agent, it will start to understand that which airport you want to fly out of, which time you want to fly out of, because you need to travel to the airport. Do you prefer aisle seat? Do you prefer a window seat? All do you have particular dietary restrictions, and it can book your ticket based on all of that. That's a very that's an interesting example, but there are many others that you can use agent for. So we're moving into a world where there's always a background process that helps your world, helps your job or whatever, right? Now, if you tie that back to your platform, that means I need to have a context that is always present and that will start to grow and grow and grow. The GPUs won't grow from a memory perspective that fast. So now we need to think about, where do I store it? Where do I store my long running context? So I start to use tiering again. So good one. GPU, CPU, fast responding storage. And now for the first time, storage, from an inference perspective, by the way, storage becomes a part of the critical path again. Where with chat, it's a web request going into a large language model, which is loaded inside the GPU memory. So there is no critical data path for storage. Now we start to store context at different layers of the platform, right? And that's where we see that there's what's called a durable state. It sits between stateless and stateful. It needs to stay resident as long as the session is working. Now, what's the end, right? So we can argue that if I do a task that takes 8 hours and once it's completed, I'm done. But there's always this history about your preferences and all that things. So that what's going to be the duration of the durable agent? That's a significant question for the next 3 years. And how is the rest of the platform start to operate and focus on these long context windows?
Yeah, and I guess the next question will be, how can you get the data to that platform in a
Yeah.
efficient and fast manner? I can imagine that that is going to be, well, somewhat problematic for some of the systems out there.
Yeah. And also think about peak. Like if I have a model and at one point a lot of agent and a lot of users are hitting that same model and I need to scale out, okay, now I need to start a new worker node and I need to load the model. I want to get that model into GPU memory as fast as possible. How can I basically expose this storage element in the most fast way possible without the least amount of detours, right? So your fast storage becomes also a critical element for scaling out at the GPU side because I can really load like I said about the bytes in memory. It's the same thing for storage. A 70 billion model is roughly around 200 gigs of storage footprint. How fast can you transfer 200 gigs to a GPU, right? That's the interesting part, what we're going to see in the next few years.
Yeah, and it's interesting because when we started out, we said that it all sounds very similar to the early days of virtualization and some of the challenges we had with VMs. And of course, storage was a big part of that as well.
Yeah.
Everyone had a shared storage platform, but those shared storage platforms back in the days were not designed for virtual machine workloads. So we started hitting all of these performance issues. And I can imagine, especially as you said, how fast can you move 100 gigs, 200 gigs worth of data, that we'll start seeing similar problems again, where that peak is going to be the issue. Not the sustainable load, but the peak will be the issue. Now, the other thing that I also wanted to bring up, and this is just me thinking out loud, you previously gave the example of those different more or less slot sizes. So you had 10 gig versus 20 gig versus 8 gig, etc. Now, one of the things that I could also imagine, especially with vGPUs, you can have multiple vGPUs allocated to a single virtual machine. So in that perspective, from a allocation standpoint and from a scheduling standpoint, would it make more sense for customers that would have, let's say, allocations of 10 gig and allocations of 20 gigs to just do 10 gigs and then allocate to vGPUs, or doesn't that make any sense? Is it just me thinking out loud and being weird as hell?
You're not the first one who asked this, right? But it's not supported to do multi-fractional GPUs at the moment.
Okay, well, that ends the conversation then. I guess I got a feature request for you, but because it feels like, it solves some of the problems, at least. If you can find a common size, then at least you don't end up with a lot of a fragmentation in your environment, which is, especially with the GPU, very expensive.
Yeah, and that can be the driving force behind that feature request. That is not necessarily that you want to add more complexity, because the distributing across multi fractional GPUs is going to be a challenge from an orchestration perspective. But from a placement perspective, it actually simplifies things, or at least it can, right? So it does make sense. However, from a uh, technological perspective, there might be a problem because you need to access that NVLink to a certain way, right? So, but let's discuss this offline. Put it that way.
Yeah, I'm not saying it's an easy problem to solve. That's what I
No,
typically tell our engineers as well as part of the vSAN team. Hey, I come up with crazy ideas. If it's
you figure it out.
difficult or easy to solve, I don't know. You need to figure that out, right?
Yeah,
And explain to PM team why you're spending all of these hours on a random project.
yeah, but I don't want to burn all my bridges for this one.
I hope Chris Wolf is not listening. Hey, thanks, Frank. Before I let you go, any famous last words or any final thoughts you would like to share with the audience?
Just try it. Just figure out a way to start trying things. Look, we're part of the VCF division, right? So we'll always say, look, try to do this in VCF. But if you can, and if you want to start to investigate the AI workload, how it will do things, there's always these resources in cloud or with your cloud partner as well, right? So you don't have to think about the entire configuration, but you can start to try, and then you can start to bring back that workload into your environment. This is one of the key things, right? Today, the frontier models, the models like Claude or an OpenAI, they are the AWS moment for the entire industry, where AWS was a competitor for every retail organization out there. Frontier models will be for everything, because there's a lot of knowledge in that environment. And so it can basically impact every type of organization out there. And so what you will see is that most customers who will start to figure that one out, they will say, I'm going to not train that beast with my private data, so I'm going to run this on-prem. And so in order to do so, you need to be prepared in order to bring that home. So yeah, try it somewhere.
And that's it. Thanks for tuning in to the Unexplored Territory podcast. If you enjoyed this episode, don't forget to subscribe and leave a review or rating wherever possible. And please join us again next time as we uncover more insights into cutting-edge solutions shaping the world of IT. Until then, stay comfortable, keep exploring.